All right, those of you at home, hopefully you're coming in here. Awesome. Everybody else in the room, get your packet, get your name on it. Get that going. We are going to start the next unit today with a little, it was usually a lab, but today it's going to be a little demo. We got the packet in front of you. These gentlemen are going to, there is such thing as perfect data, gentlemen. There is such thing as perfect data. All right. Get this going. All right. While they're doing this, let us chat very quickly for all of, and nobody came to the wrong place. Check you out, Big Chem 2 people. You guys are remembering. All right. All right. Let's take a look here at, and make sure everybody knows what's going on here. Where you at, horse? We are now starting the thermochem unit. So you will see that it's about a 4-week unit. And when the 4 weeks is done, we're going to have a nice big test on the 13th of November. You got them? All right, come on around over here real fast. Will you take the temperature of one of them? Wait until it settles. Okay. Yeah, just set it in there. Good stuff. You're feeling good too? Come on around here. All right, so we're going to start with what we usually, yeah, perfect. We would usually do this as a lab, and you would usually do this 5 times. However, we're going to do it as a demonstration, and I think that you guys should kind of be able to predict what's going to happen here. So we're at the very front, and I'll get you guys a chance to get this data. We're going to do a little experiment, okay? It's called the hot water, cold water lab, or investigations in heat change. Ooh.
Which one, cold?
Doesn't matter. Which one are you starting with?
I'm doing the cold.
Cold. Drop it in the cold for me. We have hot water and cold water up here. And what these gentlemen did is they got the exact same amount of hot water and cold water. We're going to mix them together. Hopefully we don't blow any brains, woo. Okay, but hopefully you should be good. I actually did, I have some perfect data. So we're going to go on number 2. So first thing over here. So we're starting in kind of line number 2. How many milliliters did you get of each there,
80. Sir?
All right, so he got 80 milliliters of hot. And he got 80 milliliters of cold. So let's jot that down. It's very important that it's the same amount. How much did you get?
40.
40. He got 40 milliliters of hot and 40 milliliters of cold. Now, the cold water is going to start at what temperature over here for my 80 mils? What temperature your cold water?
11.17.
11.1. Beautiful. And what's your, you want to put it in the hot now. What's your cold water going to start at?
12.6.
All right, 12.6. So that's the cold water. Pretty cold. Now, if you think this is extremely cold, remember under freezing, it's not. This is in Celsius. Celsius, okay? So we're in the packet. There's a, yeah, writing on there. We're on number 2. All right, is your hot water stop moving? What's your hot water temperature?
It's
49.9. All right, very nice. 49.9. And what's yours?
47. Right on the dot.
Oh, all right. I love a good fig on that one. All right. So now he's going to take hot water that's at about 50 degrees and mix it with cold water that's about 11 degrees. Do you have a range in your head of what type of temperature that might come to? Okay. Oh, what's happening here?
Well,
does it look different than mine?
yeah, it's got 4. You just don't.
Oh, I see. I see what you're saying. Okay, I did. Okay, my apologies there. Yeah, volume. So you're just going to write 80 for that one. Skip this line right here. Does that make sense? Skip that. So it says 80, 49.9, 11.1, 40, 47.0, and 12.6.
So, yeah.
I forgot this worksheet looked a little different than.
80 right here.
Yeah, 80.
You can write hot.
Yeah.
Yes.
All right, let's get the data so you guys can also. So what we're going to do is we're going to take hot and cold water and we're going to mix it together. The range is between 49 and 11 and 47 and 12. Ready? Mix them together, stir it with the thermometer. Tell me what temperature it settles at. Hot and cold water together. Hot and cold water together. Give me a mixed temp. Mixed temp. Yeah. Once it settles, let me know. We're now on the mixed temp column. What are we looking at? Is it still moving?
Yeah, 29.3.
29. Thank you. You can have a seat there. 29.3. And you?
30.2.
Beautiful. All right. So my apologies here. Ignore this middle column on mine. And we'll just say volume. All right. Oh, yeah. All right. So over here, we took 80 milliliters of water and 80 milliliters of water. And my hot water went from about 50 degrees to 30. Does that mean my hot water got hotter or did my hot water cool down? It cooled down, right? And my cold water went from 11.1 degrees to 30.2. Did my cold water heat up or cool down? It heated up. Does that make sense? The cold water gained energy and the hot water lost energy. Very easy, correct? Thermochem you've actually done quite a bit of. Down here, we have the exact same thing. My temperature, my hot water went from 47 degrees down to 29, and my cold water went from 12 up to 29, and they kind of met in the middle. Okay, perfect data, and we can see who has perfect data here. Should be fun. Perfect data would look a little something like this. If I had, and when I did it, I did 50 milliliters. And let's say my hot started at 58 and my cold started at 22. And when it was mixed, it was at 40 degrees. I made these numbers up in a perfect world. Okay. Awesome. So what you would do down here is I just want to take what's called the delta T or the difference. You see in your little post-lab notes down here, this little triangle in science means delta, which means change. And you might want to write a little hint to yourself. To get the change, you subtract. To get the change, you subtract. To get the change, you subtract. Okay. All right. Everybody's here. All right. Now, what I'm going to do is for my first trial, for my numbers right here, I said that my hot was at 58 and it went to 40. And I said that my cold, I'm going to skip this difference because we're going to figure that out in a set. My cold went from 22 to 40. Let's figure out how the gentleman did. He said from 49.9, so for trial 2, our hot was 49.9, and it went to 30.2. And the cold went from 11.1 to 30.2. So that was our second trial. The third trial, his hot started at 47.0 and went to 29.3. And his cold went from 12.1 and it warmed up to the 29.3. Now I'm going to do a little math and you guys can stay along with me. If I want to know how much my hot water cooled down, all I have to do is subtract. 48 minus 4, or 58 minus 40 is 18. Just because I don't want to make a mistake doing mental math here. My hot water in trial number 2 went from 49.9 to 30.2. That means it went down by 19.7 degrees. And my hot water in trial 3 went from 47.0 to 29.3. That is 17.7 degrees. Let's see how much our cold water warmed up. 22 to 40 is another 18 degrees. Ooh, nice data, gentlemen. Whoo, doggy. My cold water warmed up 19.1 degrees. That is beautiful data. Oh my gosh, this is super nice. And my cold water warmed up 17.2 degrees. This was even better than first period. I'm not going to lie. Very, very nice. The main objective behind this lab is this. And this data was awesome. Awesome. I don't know if I could have done better myself. The amount that the cold or the hot water cooled down, which is this column, should have been exactly the same as the amount as the cold water warmed up. Okay. Beautiful, 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 beautiful data there. Do you see that your hot water cooled down 19.7 degrees and your cold water warmed up 19.1 degrees? Okay. And on the next one, 17.7 and 17.2, you're talking about a half a degree difference. That is fantastic. So what you guys would have learned in this lab when you were doing it by yourself is the big idea out of this little investigative lab that you would have done is that energy lost by something. The energy lost by something. And in this case, the energy was lost by the hot water. The energy lost by something has to be equal to the energy gained by something else. Okay. Wonderful. So in your mind's eye, what you should have hopefully been seeing is it on my, and I wrote perfect data for mine. Like I didn't even really do it like that because there's really no such thing as perfect data sometimes. But if you started at 58 degrees and 22 degrees in this perfect world, they should meet right in the middle. Okay. And you guys got very, very, very close to that. That was very awesome. So what you will see, and I want you to write this down because it will kind of give you a little bit of a hint into what we're going to say. That means that the hot water's delta T, write a triangle with a T of the hot, was 18 degrees. And the delta T, remember, or the change in temperature of the cold was also 18 degrees. So when we would have done this as a discovery experiment, you would have hopefully come to the conclusion that, all right, if this cools down 18 degrees, that means this warms up 18 degrees. And as long as they measured, and I know they're good at using graduated cylinders then, because as long as they measured the exact same amount, they should meet in the middle. Okay? And then the rest of the post-lab questions for the day is like, why did we use styrofoam? Why didn't we use glass? All that kind of different stuff. So that would have led you into the lecture that we're going to do today. Okay? Just unfortunately, we're not doing labs right now. So does everybody understand? You put hot water, cold water together, they meet in the middle. Easy peasy. All right. Let's get into this. The next page in your notes. And if you care to look at the post-lab questions, they're there. These are just kind of the questions you would have had to answer. I'll put the key up if you would like, but we're moving on to the next page. So like I said, that would have been day one of the notes or of the unit. We would have done a lab. Let's move on to day two, shall we? Day two. All right. We have to talk about energy, temperature, and heat. I told you that this could be one of the hardest units, and it is the hardest unit in the first semester. And the reason why is because people bring misconceptions in, and there's a lot of math once we get started. But for right now, today, you might know some of this stuff and you might not know some of this stuff, but we're going to get everybody on the same page because this is where misconceptions start, okay? So energy, overall, let's first talk about kinetic energy. Kinetic energy. Kinetic energy. kinetic energy. Who can tell me? You probably have from somewhere. Kinetic energy is the energy of what? Because you have potential and you have kinetic. Kinetic energy is the energy of moving objects. You probably remember that from somewhere in your science career. The energy of moving objects. Now, if I tell you that this calculator has kinetic energy in it, I'm talking like I got to chuck it across the room. What is moving in this calculator that gives it kinetic energy? The atoms, the particles, things like that, okay? Boop. So when I talk about the kinetic energy in a substance, I'm not talking about the whole thing moving itself. We're talking about the particles. So if I'm talking about in this ice water, it has a low amount of kinetic energy. Does that mean the particles are moving fast or slow in here? It moves slowly if it's low temperature, okay? The faster it's moving, the more energy something has. And in chemistry, we're talking about particles. Okay, put your hand on your desk. Can you feel the particles moving? You cannot. But they are there, and they are vibrating in place in a solid. Okay, so we're talking about, when I say energy of motion, I mean the moving particles inside of your matter. Okay? All right, so now that we did a background on energy, we got to talk about thermal energy. Thermal energy is the total kinetic energy of all the particles in a substance. The total energy of all the particles in a substance. The unit for thermal energy is called a joule, Joule. And the unit you're going to use for it, if you just want to write it like, kilometers is km, is a capital J. And no, it's not joules like gems. This was somebody's last name. When you find something, you can name it after yourself, like Bay units or whatever. Okay. Now, the thing about thermal energy, and we are going to calculate it a lot. This will be your favorite equation. Q is equal to MC delta T. You probably are like, I know what delta T is now. I'm halfway there. M is going to be mass. When you're calculating thermal energy, mass is extremely important. So you need to know that thermal energy is actually extensive. That means the more you have of something, the more thermal energy you can have. So an interesting side conversation on this. Let's pretend we have an iceberg with 1 million liters of ice. And this picture is not on your packet, so we're just looking. And that's at 0 degrees Celsius. Okay. And then you have a cup of boiling water for tea or something. And let's say that's 1/4 of a liter, which is still a pretty large drink. Which one do you think, if you count all the particles up, even though this one is hotter, this one has 1 million liters in it? Which one do you think has more thermal energy at the end of the day? Let's pretend we didn't have COVID and we could go down to the shoe down on Ohio State's campus and you could shout just as loud as you could, like, ah, like just screaming, okay? But then let's pretend that we had 1 million people in the shoe and they were all kind of talking just at normal level, but they are all talking at the same time. What would be louder? 1 million people talking or one person trying to shout? 1 million people talking, correct? So when you're looking at thermal energy, the mass matters because what has more thermal energy in it? An iceberg. Okay, the cup of water might be hotter, but there's not enough particles. It is extensive. That means it changes with mass. Okay, so thermal energy is the total. You have to take into account the mass. Are you with me? All right, let's take a breakdown real fast, and I want to spend a moment talking about something that you guys probably already know. I believe that these standards are in the middle school level, and I think they're in the physical science level, but I want to make sure everybody's on the same page just in case I use these terms. First way that thermal energy can move is through the term conduction. Conduction. Conduction is the transfer of energy through contact. Okay, it must be touching. If you are going to conduct energy, you have to have a touching, particle to particle. So if I wanted to conduct energy from my hand into this cold water, I would need to touch it, and then I would feel the transfer of energy. Okay, conduction. Convection is the transfer of energy in a gas or a liquid. Convection is the transfer of energy in a gas or liquid by movement of currents. Probably when you learned about this, you learned about like the macaroni and cheese boiling and sinking and boiling and sinking, and it heats and then cools and then heats and then cools. And then the last one is called radiation. Radiation. And that's when you have electromagnetic waves that go direct. You transport energy directly through a given space. You don't need any particles. Okay? Transports energy. This is how the sun gets energy to the earth, because what's between the sun and the earth is called outer space, because it's just space. There's nothing in outer space. Okay, so in order for energy to get from the sun to here, so if you ever see this on like a test or a standard test or anything like that, radiation is always more talking about the sun or talking about heat from like a fire. Okay, those are some hints on when it is radiation. Okay, so we have our little pictures over here. We're going to try one more time here. If you touch direct contact, that is conduction. Conduction, like a conduction stove. You have to have the pan touching the hot surface. It's not even hot, the surface. Energy transferred by the motion of molecules is convection. And on the side here. Good. And then my little picture over here. Energy transferred by electromagnetic radiation is radiation. So there's a little picture to help jog your memory on each of those. Hopefully those are things that you have already seen. But I thought I'd refresh those. Okay. Questions so far? Almost done. Get in there. We talked about in the last unit the law of conservation of mass. There is also a law of conservation of energy. Like we talked about in the lab, when this hot water cooled down and this cold water warmed up, where did the energy come from to heat up the cooled water? From the hot water, and vice versa, right? This lost energy, this gained energy. And we just wrote it on your little thing here, but it's called the law of conservation of energy. You cannot create or destroy energy. You cannot create or destroy energy. So the heat gained by something is equal to the heat lost by something else. So this cold water didn't get warm just because it felt like it. It got warm because you put hot water in it and they came together. This is going to be a huge, huge, huge idea in math in this unit. Okay, so we're going to come back and do a lot of math with this idea. Okay, and don't forget the law of conservation of mass. He's there. Doesn't hurt when you're talking about conserving things, that you cannot create or destroy mass, and you cannot create or destroy energy. Okay, all right, let's move on. So we talked about thermal energy, and now we're going to talk about temperature. Some students really have an easy time confusing those, and let's try to see if we can't make it a little bit simple. Okay, when I take this temperature and I put it into this cold water, does this thermometer know how much water is in here? It doesn't. If I want to take the temperature of the air, a little cold, but that just came out of there. Does this thermometer know how many particles are in the air? How does a thermometer work? Well, what happens is particles are moving around you all the time, right? The air particles are moving and they're hitting this thermometer. If they hit the thermometer faster, the temperature goes up. If they slow down and don't hit the thermometer as much, the thermometer reads cooler. Perfect, okay? But so that little thermometer can't tell me how much it is measuring. It just tells me how fast the particles are going, right? So the idea is that this is temperature is the average amount of kinetic energy. It is about how fast the particles are going, but you can't tell me how many. The average kinetic energy of the particles. So all you can tell when you're doing temperature is about how fast the particles are moving. Are they moving fast, making it hot? Are they moving slow, cooling it down? So I guess if you want to write that down, we can. So if they're moving fast, it's hot. And if they're moving slow, it's going to be cool. So when I put this thermometer in this ice water, how fast do you think the molecules are moving relatively? Are they going fast or are they going slow? They're going slow. They're not hitting it very fast. You're getting a low temperature. Okay, awesome. The units for temperature in this class are degrees Celsius or Kelvin. Degrees Celsius or Kelvin. And just the conversion we'll have to use some other time is if you have degrees Celsius and you want Kelvin, all you have to do is add 273. You add 273. Yeah, if you have Celsius, you add 273 and that gets you Kelvin. We'll talk about that more when we're talking about using it in a mathematical equation. Kelvin, if you haven't heard of Kelvin, if you took the 9th grade physical science, you might have. Kelvin is a scale that includes absolute zero. Absolute zero is a temperature in which it is so cold, it's 273 degrees below freezing. It's so cold that the particles actually stop moving. Now, we've never really reached that. We don't know exactly what happens when you get there. So that's why we use the Kelvin, because it can get very, 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 the particles can move very, very, very slow when you approach absolute zero. The problem with absolute zero is matter is defined as stuff that is made of moving molecules. And if you stop moving molecules, do you have matter? I mean, who knows? It's crazy. So that's for very intelligent people to figure out the answer to. The other thing about temperature, you guys are going to answer this for me. Okay. This is 12.6 degrees. Ready? I'm going to pour some out. What do you think the temperature is now? 12.6 degrees. What if I pour some more out? What do you think the temperature is now? 12.6 degrees, right? So does the amount matter to the temperature at all? No. Then remember your word from the last unit, that means it's intensive. So mass does not matter. Okay, temperature is just an average. Wonderful. So that's thermal energy and temperature. Those are very easy to confuse. Remember, thermal energy has to do with mass. Temperature is just an average. All right, let's get to the back. The last term is where most of the misconceptions come along, because heat is a very misunderstood word scientifically. Heat, okay? Heat actually just simply refers to the transfer of thermal energy. People think heat is always as hot, which is okay with me because there is no cold, but you're actually talking about the transfer of thermal energy, okay? The units for heat are either joules or calories. One of the labs that we usually do is we get a bunch of snack food and we light it on fire and we burn it. And I don't know if we're going to be able to do that this year, but you could calculate how many calories are in it by burning it. Because when you eat it, you do the same thing. You burn it. The biggest misconception in heat is that people think if I were to put this on your skin and it feels cold, listen to me. Cold is not a thing. It is just a definition of a feeling. When I put my hand on here, there is no cold applying to my hand. what is happening is that this is at a very low temperature. I'm at a very high temperature, and energy is leaving my hand and going into the water. That is a huge misconception. People think that like when you go outside and you're like, oh my gosh, the cold is getting me. Cold isn't getting you. You are losing thermal energy because of this. You must speak in the direction of heat, not in the direction of cold, because everything goes, where am I at? Where am I at? Always, where's my high and low? Oh. Okay. Coldness doesn't exist. It's just a lack of heat. And I skipped one thing, and that's okay. I'll come back to it. Okay. You always speak in the direction of heat, not of cold, because cold is just a lack of heat. Now, let's talk about whether heat is intensive or extensive. Before football got all weird, nobody's allowed to watch it. Let's pretend we're watching the Super Bowl last year. Okay. Once the team is about to win, what do? They go find a thing of Gatorade with ice in it, right? And then they run after who? The coach. And then what do? They dump it on him, right? In the idea that they want to transfer some energy from that poor coach's body, right? They get a big thing. What if they're like, guys, I got him. Okay, I got some ice water up here. I'm going to get, got you, coach. Would this cool that man down at all? No. Why do you think they get the biggest amount of Gatorade that they can find? And they want to dump a whole bunch on them because when you're trying to transfer energy, mass matters. So heat is extensive. Mass matters. Okay? It depends on how much you have. If you're like, hey, I'm going to, cool this kid down. I'm going to put like one little ice cube on him. Like that's not going to do anything. If you want to transfer a lot of energy, you need a lot of mass. If you get a little bit of boiling water on your hand, you're like, ouch, that hurts. But it's okay. It didn't transfer a lot of energy. But if you put your hand in boiling water, like a big pot of it, you're going to have a problem. Okay? So heat or the transfer of energy does matter with mass. The other two things, and I think you know these, I'm not trying to insult your intelligence, but we're just getting on the same page today. Something that is called a conductor transfers heat easily transfers energy. We're talking about metals. We're talking about glass. Okay, wires, which are made of metal. Conductor. If it's not a conductor, it can be what's called an insulator, which resists transferring energy. What is this cup made out of that they used up here? Any idea? Called styrofoam. Wood. Your other conductors or your other insulators on your cups, things like that. Okay. So I am assuming that you guys know what a conductor and an insulator is. So hopefully we can use those terms. So hopefully you know. Conductor quickly transfers energy. Insulator slowly or resists transferring energy. Okay. The last thing that's kind of challenging sometimes is you have to do what are called energy diagrams. And the biggest thing with an energy diagram and why we say that cold does not exist is because nature's tendency, everything goes from an area of high temperature to an area of low temperature. Everything goes from an area of high temperature to an area of low temperature. So I kind of have really big down here. Everything goes from hot to the lack of a better word, cold. Everything goes from a high temperature to a low temperature. So when I put my hand on this ice water, energy is going from my hand into the water. Nothing is coming from the water. It feels cold because that water is stealing energy from my hand. Let's have you guys do an example yourself, and then we're going to fill this in together. Got that? Perfect. Take one hand. Those of you at home, you guys can also try this. Take one hand and put it on like the wood of the table. The wood of the table. Yeah? Take the other hand, put it on the metal leg of your chair. Ooh. How does that feel? Okay. Does one of them feel particularly cold? Which one? The leg of your chair, right? I have a question. the table and the chair have been in this room all weekend, right? They've been in here all morning. And I promise I haven't gone around and like heated up your tables or anything. Is the table and the chair at any different temperature? Or are they both at room temperature? What do you think? Neither of them, so it feels colder, but they're both at the same temperature, correct? So the idea here is that they're both at the same temperature. So why does the chair feel cold? Think about some of the terms we just talked about, and the table feel warm. Tell me. Perfect. The metal is a conductor, but the wood is an insulator. Now, I'm going to show you how I expect you to draw energy diagrams. Are you ready? And so go ahead, draw yourself, because it says, please draw an energy. Oh, we can answer the question first if you would like. They feel different because the chair is metal, which is a conductor, like you said, very good. And the table leg is an insulator. Now here's, and if you just write chair, metal, conductor, table, wood, insulator. When you do an energy diagram, you have to tell me the direction of heat. So let's have you just go ahead on your paper and draw a chair, even if it just looks like this. Beautiful chair. Draw yourself on that chair. I know I should have been an art teacher. And then draw yourself a table, even if you just draw a square with 4 legs. Are you ready? Let's do an energy diagram, my peeps. In Celsius, okay, you're about 36, 37 degrees. So we'll say 37 degrees Celsius. That is you, okay? If you don't have a fever. And around the room, a comfortable temperature for most people in Celsius is about 23 degrees Celsius. And so that means that both the table and the chair are the same temperature. What is hotter, you or your chair? You. So we're going to put a little high. You are an area of high thermal energy. The chair is an area of low thermal energy. And in that arrow diagram right above you, everything goes from high to low. Okay? So energy is going from you to your chair, and energy is going from you to the table. It just so happens that on the chair, it goes quickly. And on the table, it just goes slowly. Okay? So that is the only difference. And that one, it goes quickly, and one, it goes slowly. Okay? So when you have this worksheet, let me see, the next page is a worksheet. For instance, in the morning, when you walk into the bathroom and you step on the tile, what does it feel like? It feels cold. So you jump on the rug. Are either of those two, unless you have heated floors, and then I'm jealous, are either of these two things at different temperatures? No. You are hotter than both of them, and they're at the exact same temperature. But why does the tile feel colder than the rug? Because it's a conductor, and it quickly takes your energy, and the rug slowly takes your energy. Okay, so I want you to work on this worksheet tonight. Open up your Chromebooks. You got about 3 or 4 minutes, maybe 2. You have some post-lab questions. I would keep your notes out while you do these post-lab questions. And the last thing, I have a little demo. Don't go anywhere. Can you see who is here? I'm not going to have time to take attendance while you're on there. Can you just? Awesome. All right, so here's a little example of convection that you can do at home. What I did was I took a bag of tea, and I actually cut the bag of tea, and I just emptied the tea out. And it was interesting because it's usually folded in half like this. If you cut the top off, it's actually a cylinder. Okay, so what I'm going to do is I'm going to take this cylinder, the outside of the tea, and I'm going to light it on fire. Okay. And this is something you can do at home. It works better with like nicer tea. As that's burning, I'm heating up the air inside of it, and then it will all of a sudden take off. Okay, so we heated up the air. The air is going to heat as it rises, and then it cools. This lovely little piece of tea. Come back. You don't want to really mess with it too much because, so the rest of the tea bag is now falling back down as it cools. Okay, so a little convection. If you drink tea, kind of take the tea bag and do that. It's kind of fun. So you guys are going to do your post-lab questions. You want your notes with you while you do that, okay? Perfect. Thank you, guys. If you need to do your questions later, you can.